topic, which is bipolar junction transistors and small signal model. So we've looked at DC model for a bipolar junction transistor, and in an earlier lecture we had done a little bit on small signal model, but let's continue our discussion. So as a motivation for small signal model, we had seen in the last lecture this particular circuit here, and we said that this particular circuit can amplify, and we saw that you need to bias the transistor in forward active mode, and so these voltages VBB, RB, and VCC and RC, these are all used to bias the transistor at a particular point in the forward active mode. And then on top of that, if you apply a voltage here, a signal, that signal then goes and travels to the base here, modifies the base current, modifies the base emitter voltage, which causes a modification in it causes changes in the collector current, and that results in a sinusoidal or a voltage which is proportional to the signal here. And if you bias it properly, if you choose all the resistors properly, you get amplification here. So the way we find out amplification is, as you can see here, when we are talking about amplifiers, we are interested in knowing what is the effect of this input voltage here. That's a small incremental voltage that we have applied here, and we want to know what is this impact at the output here. So the way we do it is, whenever we have an incremental voltage or a small signal voltage here, we build a small signal circuit. And the way we build a small signal circuit, as I've said, we have discussed in some detail earlier, what will happen is that the voltage source that you see here, that will get shorted. DC source will get shorted here. This source will get shorted here. Resistors will remain resistors. And so what we'll end up with, something like this here. Okay? Where DC sources have been removed, because we are talking about incremental values. We are talking only about what is the impact of this voltage on the, let's say, the current here and the output voltage here. And what I've shown here is that we need to replace this transistor Q1, just as we replace every element by incremental model or a small signal model. We need to replace the transistor also by a small signal model. And if I do that, if I replace the transistor also by a small signal model here, then I'll get a circuit which is a linear circuit, and if I solve it, I'll get V out here in response to V in here, and if I take the ratio, I'll get the voltage gain. And similarly, I can get other properties here. So you realize that if you want to go forward in analysis of amplifiers, you would require a small signal model of your bipolar transistor here. Alright. So in an earlier lecture, we had seen that if you have a three-terminal device here, three-terminal unilateral device, meaning that the signal propagates from input to the output doesn't have any effect on the input here. Okay, so it's unilateral. And if you have a device like this, then is small signal model is over here, given in this part of the circuit here. And what you see here is, from the input side, your three-terminal device appears as a resistor Ri, and from the output side, it appears as two elements. One is a voltage control current source GMVI here. That denotes the fact that I0 is dependent on Vi. So that gives rise to this element. And I0 is dependent on V0. And that gives rise to this particular one. Okay. So these are the elements that you get here. And we had seen that you can determine the values of these elements. Ri will be given as the derivative of current with respect to input voltage here, inverse of that. So that's Ri. GM is, as I said, we are talking about small signal or incremental models, so it denotes change in I0 with respect to change in Vi here. And R0 talks about change in I0 with respect to change in V0 here. So these are, once you know the expressions for I0 in terms of Vi and V0, it's straightforward to take a derivative and determine what the values are. Okay? And so all of these values can be determined here. So let's come back to a bipolar transistor. It's similar. From the input side, we have the base current and the base emitter voltage. From the output side, we have the collector current and collector emitter voltage here. So, yes. R0 should be dV0. Yes, you're right. This should be okay. So that's an error here. Let's see. Yeah, this should be V0. Okay. Correct. And so, coming back to this bipolar transistor then, for this transistor, note that input is, so we are taking emitter as a common terminal, collector is over here, base is over here, and therefore between base and emitter, I will get a resistor in correspondence with this resistor here. We have a specific name, we call it R pi. And from the output side, we get IC, we get a term here, GMVBE here in correspondence to this term here, and we get an R0 here. Okay, so same, exactly the same model that you see here. We see something similar here over the side here. Now, we already have an expression for IC in terms of VBE, and we have expressions for IB in terms of VBE. And so all we need to do is take those expressions, take the derivatives, and get the values here. Okay, so this is something that we already have. IB is IS by beta F exponent VB by VT minus 1. Note that between base and emitter, I have a diode. So my current, base current, is exponentially related to base emitter voltage here. So all I need to do is note that this is the, so I need to take the derivative of this one with respect to base emitter voltage here to get R pi. So if you do that and simply ignore the minus 1 because base emitter junction is forward biased, so you end up getting R pi is 1 over R pi is IB by VT, or R pi is VT by IB. And then of course we know that IC is equal to beta times IB here, so we can get R pi is VT by IC times beta. Okay. And by the way, we are developing this particular model only for forward active mode. Okay, so that's why I'm using this relationship IC is beta IB. This model is only for forward active mode. Now you could build it for saturation mode as well, and the you know that in saturation mode what will happen is your output of course is affected by input, but then because you forward bias this junction, what will happen is the input will also get affected by the output here, and the expressions for collector current and all that change. So the model that we are right now developing is only for forward active mode. Sometimes this R pi that you see here is written as RE times beta here. The first term VT by IC is what we call as RE, and beta is here. Okay. So IC is, we have seen this expression here. If I take its derivative with respect to VBE, so we get GM del IC by del VBE here. We get approximately equal to IC by VT here. Approximately where to calculate GM, I've neglected this particular factor here. Okay, IC by VT here. And R0 is del IC by del VCE, output voltage here. That turns out to be IC plus VC plus VA. And early voltage is much larger, usually as compared to collector emitter voltage here. So one can approximate it as IC by VA. So these are the, so that's the model that we have then. Okay, that's the model that we have. So whenever we see a bipolar transistor, what we can do is we can replace it. If we are doing small signal analysis, we can replace it by this very simple model here, R pi, GMVB, R0. And this is how we determine these quantities here. So note, R pi, to determine R pi, GM, and to determine R0, what you need to know is the bias current here. So before you do small signal analysis, you have to do a bias point analysis. Okay, and after you do a bias point analysis, you know where your transistor is operating, then you know IC already, so you can substitute and determine R pi, and therefore GM and R0 all depend on IC. Okay, so you can determine all of these quantities. A small signal model is of course obtained by a process of linearization, and what we linearize in this particular case is that, note that IB is exponentially dependent on VBE, so we are linearizing this and approximating it by R pi. Similarly, IC is the collector current is exponentially dependent on base emitter voltage, so we are linearizing it and getting a linear element here. So we are linearizing an exponential and obtaining a linear element R pi and GMVBE. And obviously the approximation will be valid for small values here, and one can show here that as you approximate your exponential by linear, what needs to be true is that the base emitter voltage, small signal base emitter voltage, has to be much smaller than the thermal voltage here. How small, again, we have seen, depends on how accurate an analysis you want to carry. Okay, so this voltage has to be much smaller than thermal voltage. Thermal voltage, all of you know, at room temperature is 26 millivolt. So which means that base emitter voltage that you see here has to be considerably smaller than thermal voltage here. So we are talking about, if this is 26 millivolt, we are talking about maybe 1/5 of this value here, 5 millivolt, 2 millivolts, 1 millivolt. Again, it all depends on how accurate an analysis you want to do here. So this base emitter voltage has to be small in order to carry out use this particular model here. As the base emitter voltage gets closer and closer to VT, the error in this particular model becomes larger and larger. Okay. All right. The other point is bipolar transistor. Let me add. So the other thing is I've written here low frequency because so far I have not considered any capacitance inside the device. Once I look at capacitances and if I add capacitances to it, then the model will be valid for any frequency, high frequencies as well. Okay. Before I leave this small signal model, one point I want to illustrate is my bipolar transistor is not strictly unilateral. Unilateral in the sense we said unilateral means I naught is affected by input, but input current is not affected by output here. But in fact, input current is affected by output. The only thing is the dependence is very small here. So if I want to be more accurate, more general, then I should write that input current is a function of Vi here and a function of V0. If I were to do that, then if I look at my model, small signal model from the input side, then what I will need to do is I need to take the change delta I here, incremental change in current. That will be equal to a term due to incremental change in Vi and a term due to incremental change in V0. That will be the incremental change in current here. This we can write the first term note is del Vi is nothing but small incremental voltage Vi here. So I can write this as Vi by Ri. The second term that you note here, this is del V0 means the change in output voltage. So this we denote by V0 here. And don't go into the details. Suppose I say that this is negative, so I'm going to write it as minus V0 by Ri0. Okay. All right. So this input current then, the first term corresponds here, and the second term corresponds to here. Okay. As I said, suppose this term is negative, accepted. If that is true, then I can write this as V0 by Ri0, and I put a minus sign so that Ri0 is also a positive quantity then. If you know that this term is negative. Okay. Now, if I look at this one and I want to represent it in the form of a circuit, one way is if you look at it, Vi by Ri will turn out to be a resistor here, and V0 by Ri0, I can't represent it by a resistor here. I'll have to represent it by a voltage dependent current source. A voltage dependent current source. Because from the input side, if you want to put an element here, right, which represents this one, then the only way to do that is by a voltage dependent current source here. Okay. So I could do that, but I want to write it in a slightly different way. If you look at this expression, Vi by Ri, I've added a minus Vi by Ri0 plus a Vi by Ri0. So I've added a negative term and I've added a positive term, so it doesn't change anything. And then I've made an approximation. And the approximation that I've made is that my Ri that you see here is much smaller than Ri0. What does it mean? It means that my input current depends a lot on Vi, doesn't depend too much on V0 here. Right? Because if input current doesn't depend too much on V0, it means my Ri0 is very high. In the ideal case, Ri0 goes infinity and the second term goes 0. Okay? So this resistance that you see here is much larger than this Ri here. So when I look at the first term, in the first term, Vi by Ri and minus Vi by Ri0. So I can neglect Vi by Ri0 in comparison to the first term here. So I just write it as Vi by Ri. And the second term is Vi minus V0 by Ri0. Okay, so it's just an approximation. And so first term, I can write it as a resistor. Note, first term, I can write it as a resistor. This is nothing but Vi by Ri. Input current I equal to Vi by Ri, so I write it as a resistor. The second term, Vi minus V0 by Ri0, it means I can denote it, this is Vi, this is V0, and the current flowing through this is Vi minus V0 by Ri0. So what one is showing is, if you want to be exact, then this term should have appeared here as another element in parallel to Ri as a voltage control current source. But as an approximate, keeping in mind that Ri0 is much larger than Ri, you could alternatively include this effect by adding a resistor here between these two, equal to Ri0. Okay, and the error is not going to be too large because, as I said, Ri0 is much larger than Ri. Which means what? That the fact that my device is not strictly unilateral it results in another resistor here. Okay. As I said, ideally, if the device were unilateral, then RIO will go to infinity and this term would be absent. So in a bipolar transistor, what it means is that in addition to this resistor here, you also have this particular resistor here. So a better model that you see sometimes in books is that in addition to R pi, GMVB, R naught, you have R mu also. This resistor also. So if you want to be very accurate and do the analysis, include R mu also, but you will find that R mu is 2 or 3 orders of magnitude larger than R pi. And R mu is not only much larger than R pi, it's several times larger than R naught also. Okay, so it's a very high resistor, and in most applications, what we do is we neglect this particular term in most of the cases here. So I'm pointing out to you that in a small signal model, R mu is there, but what we will do is, in almost all the analysis, we'll assume that there is no coupling between the input and the output through this R mu here. This R mu is very high, close to, so we'll assume it to be infinity and neglect. Okay. The other point is, we said that the device is not strictly unilateral, which means that the input current depends on output voltage here. Where is this dependence coming from? So very quickly, what happens is the following. What we are saying is the base current then, when we say device is not unilateral, we say that the base current depends on the collector voltage, right? The base current here does depend on the collector voltage. So if I go inside the device, what I find is that base current is coming from here, is coming from this terminal, and this terminal, this whole region is p-type. So the aim of this particular current is to supply holes, because this region is p-type. Now, it supplies holes, so the idea is, where do these holes go? Well, we have seen that the junction is forward biased, so the holes go here. That's one place where the holes are going, and the purpose of base current is to supply those holes which are going here. Now, another place where holes are required is, we have said that the electron starts from here and goes all the way to the collector. But some of these electrons, as they come into the base, these electrons find a lot of holes. P region is full of holes here. So some of these electrons will recombine with the holes here. Very few, but some of them will recombine with holes here. Now, every hole that is lost due to recombination, that has to come from the base here also. So in steady state, what happens is, the base current that you see here has two components. One component is here, that goes into the emitter. The other component is which supplies the recombination. All right, recombination here. So now if we keep in mind that the base current has these two components here, IP, which is this whole current here, and IB1, which is this recombination here. Now, obviously, you can see that recombination current would depend on the thickness of the base here, effective thickness of the base. The longer the base is, the more chances are that the electron injected recombines with the holes here. So IB that you see here will proportional to base, the neutral base here, right? This part here of the region here. Now note that as I change my collector voltage here, we have said that the depletion region becomes larger, and therefore my base width changes. Base width changes. So now you see how my base current is becoming a function of collector voltage. As I change my collector voltage, what happens is this depletion region that you see here, it becomes larger, and the base width becomes smaller, and therefore my current, that IB1, becomes smaller. And therefore what you are seeing is that base current, overall base current, starts depending on the collector voltage. So that's where the dependence of base current on collector voltage is coming. Okay? Again, as you change the collector voltage, you change the depletion width here. And as you change the depletion width, you change the effective neutral base region here. And as you change the neutral base region, you alter the amount of holes which are recombining. And as you alter the amount of holes which are recombining, you alter the base current. And thereby you get IB, which is dependent on collector voltage here. But as I said, this IB predominantly is due to, in most transistors, is due to this whole current here. This current is small. And therefore, the dependence of base current on collector voltage is also small. Okay, and in most cases, we'll neglect it. Alright, so keep in mind that R mu is there, but its value is large, so we'll neglect this particular quantity. So our model then remains that we'll continue to use a small signal model, which has R pi only here, GMVB here, and R0. Okay, so that's the model that we'll use. The other thing that we need to add now is add capacitances. to my model, and thereby we'll get a high frequency model. Okay, so let's look at the capacitances. While talking about capacitances, keep in mind that anytime we have a charge which changes with voltage, we have a capacitance, right? So we have C equal to del Q by del V. All right. There are two kinds of charges in a semiconductor. One is a depletion charge, which comes about due to ionized donor and acceptor atoms, and a diffusion charge, which comes about because of excess electrons and holes. Okay. So let me remind you, if I take my bipolar transistor, I bias it in forward active mode. What happens is, I get it. In any case, whether I bias it or not, between emitter and base, I have a depletion region. Okay, depletion region here. So that's referring to the depletion charge. Not only that, I have a depletion region here also. Okay, this is the collector-based depletion charge. This is the emitter-based depletion charge here. So that's the charge that I'm talking about. Now, we know that as I change my emitter-based voltage, this charge is going to change. And therefore, I will have a capacitance. And similarly, as I change my collector base voltage here, this charge is going to change, and therefore this will result in a capacitance. So that's the source of depletion capacitance. Okay. So note, I've added two capacitances here. This CJE, what do I mean by that? C, junction capacitance. J refers to junction capacitance or depletion capacitance. E refers to associated with emitter base junction. This is CJC, associated with base collector junction here, and junction of course refers to the junction here. So I have two capacitances corresponding to two depletion charges here, base emitter and base collector. Okay, and so we are going to put this capacitor across between emitter and base, and this one between base and collector. So these two capacitors are easy to see here. The other one, okay, so how do these vary? Depletion with change with voltage here. So this is the expression that one needs to keep in mind. This capacitance CJE is equal to CJE0, 1 minus VB by VBI times M here. CJE refers to, O refers to the capacitance here at zero bias. When you put VB equal to 0, you can see CJE equal to CJE0. VBI that you see here is the built-in voltage of this junction. And M is a factor which is related to how, what is the doping profile in this one here. So anyway, these terms will be given to you. CJE0 will be given to you, VBI will be given to you, and M will be given to you. Which means that if you know the base emitter voltage, you can determine the junction capacitance. And note, because the base emitter junction is forward biased, so most of the time what we'll assume is VBE for us is about 0.7. So we'll assume it to be 0.7. If VBI is given to you, we can quickly calculate what the junction capacitance is. Yes. VBI will also be given to you. VBI is the built-in voltage, which means that when you don't apply any bias, there is a depletion region here, and there's an electric field. And if you integrate the electric field, there is a voltage across. So that's the built-in voltage inside the junction. Okay. The other one, CJC, is exactly similar. This is also a junction capacitance. So CJC is same, CJC0, 1 minus VBC by VBI to the power n. Now VBI for this one can be different from VBI for this one, because the two junctions are different. Okay, although I've written VBI as same, the two junctions are different. So you can have VBI C here referring to collector junction, and VBI E referring to base emitter junction. Okay, so these two capacitors can be easily calculated once you have the voltages here. Diffusion charge, as I said, is a charge that comes about because of excess carriers. Excess carriers stored in these regions here. So when I forward bias my emitter base junction, we know that what happens is electrons are injected here. Electrons are injected into this region here, and holes are injected into this particular region. Okay, holes are injected into this particular region here. Now I've not shown holes here. The reason being is the emitter is heavily doped and base is lightly doped, which means that a lot more electrons are injected here and much smaller number of holes are injected here. So when I'm looking at diffusion charge, most of it is in the base. Okay, so that's the charge here. And as I said, anytime you have a charge and it changes with base emitter voltage, you have a capacitance here. So that's the source of this capacitance. This charge, excess electrons that have come from the emitter, they are stored here. And as I change my base emitter voltage, if I increase my base emitter voltage, more charge comes in. If I decrease it, less charge is there. and therefore I have a capacitance, and this capacitance is between base emitter voltage here. Why? Because it responds to base emitter voltage here. As I change my base emitter voltage, the charge here increases or decreases. Okay, so I have this capacitance again, which I call it as the diffusion capacitance here. There's no diffusion capacitance with respect to collector base junction because it's reverse bias. It doesn't inject anything. Okay, so I don't have any diffusion capacitance associated between these two. If I were doing for saturation region, then collector also injects, and then I would have a diffusion capacitance here also. But since I'm building the model for forward active, diffusion capacitance is not there in this region. Okay, diffusion capacitance depends on IC by VT times tau f. Tau f is another parameter called transit time, base transit time here, so C diffusion you can calculate if you know what is the collector current. Tau f again will be given to you. It depends on how the transistor is made, so it's a well-defined parameter of a transistor, and you can obtain it from the data sheet that the manufacturer supplies you. Okay, so that's the diffusion capacitance. What is important is, if I look at all the capacitances in my bipolar transistor, the largest capacitance often turns out to be is this one, C diffusion. That's the largest capacitance here. Often, as I said, largest capacitance here, and therefore, when we talk about, we'll soon see, when we talk about speed of a transistor, the speed of a transistor depends on the capacitance. The smaller the capacitance, the higher the speed. Because note that it's only if I don't have a capacitance in my system, then everything in my system will respond instantaneously to voltage. You know, as basic elements, you have resistance, you have capacitance and inductance. If you have only resistances in your system, then it means that it has infinite speed. It responds instantaneously to any change in voltage here. It's only when you have a capacitance that you find that you can change the voltage and the current does not respond instantaneously. It takes time. Okay, so speed of a transistor, the reason why transistor has a finite speed is because it has capacitances. And the smaller the capacitance, the higher in general the speed of the transistor here. Okay, so now if I tell you that the largest capacitance in my bipolar transistor is diffusion capacitance, then what I want is the faster bipolar transistor will have a smaller C diffusion. And if you look at C diffusion capacitance depends on IC by VT and depends on tau f. IC by IC, of course, depends on my biasing. So if I take two different transistors and bias them at the same collector current, then their diffusion capacitance will differ primarily in tau f, how they have been made. And if I go and examine tau f, the base transit time, if I go and examine it, I find that there are several factors on which it depends. Two of them I've highlighted. One is base width here, the thickness of the base width, and also depends on the mobility. Okay, so what it tells us is, if you want a smaller diffusion capacitance or a faster transistor, what you should look for is a smaller transit time. And a smaller transit time you get by making the base thinner. Make the base as thin as possible, and by using a material or a carrier which has higher mobility. And that's why you find that NPN transistors are usually preferred for higher speed as compared to PNP. The reason being is, in NPN is the electrons which are moving here, and electron mobility is higher than the hole mobility. In a PNP is the holes which move here, and the hole mobility is lower, and therefore transit time is higher, and therefore the capacitances are higher and the transistor is lower. So NPN transistors are faster as compared to PNP in general, other things remaining the same because of this higher mobility. And the smaller the base that you make, the faster the transistor becomes here. What does? Transit time, well, one way of looking upon it as the amount of time it takes for an electron to travel across in this region, from this end to this end. That's the base transit time. Okay. These things are just being stated. The tau f is WB squared by mu, C diffusion is IC by VT. The derivations for all of these will be done in a subsequent course, 311. For us, what is important is that there is a capacitance here. That capacitance has a large value. much larger than the other capacitances. And how do we calculate it? And we know that calculation is very simple. All I need to do is C diffusion is GM times tau F. If I know tau F, I can calculate C diffusion. Yes. Larger the speed, well, if you take, say, RC circuit, simple RC circuit, right? You have an R and a C. And what is the frequency, cutoff frequency for an RC circuit? 1 by 3 dBs, 1 by 2 pi RC, right? So if R, everything else remains the same, which is a faster RC circuit? If 3 dB frequency is 1 by 2 pi RC. So the smaller the capacitance, okay? So it comes from there. We'll see when we look, when we go further in this course, we'll look at the frequency response of the amplifier, and you'll see how frequency response depends on tau. So you'll see why, which amplifiers are faster and which are slower, and it does depend on tau. But that's a simple picture because it depends on many other things also. It's not just tau F, it depends on other things as well. Okay. So this is a picture of capacitances in a bipolar transistor. I have across the base emitter junction, I have two capacitances. CJE is the junction or depletion capacitance, and CD is the diffusion capacitance. Both of them come in parallel. Okay, both of them come in parallel, and CJC is the capacitance across the collector base junction. This junction is not forward biased, so I don't have a diffusion capacitance. Okay. There's one more capacitance which you don't see in this particular picture here. This picture, if you recall, when I showed bipolar transistor for the first time, I showed that this is a simplified schematic. The actual bipolar transistor is not one-dimensional that you see here. It's a two-dimensional. Actually, it's a three-dimensional, right? So I was showing you a cross-section. Let me show it to you once more again. Okay? So this is the picture that I put. Now you can see that the capacitances that I'm talking about is one across the emitter base junction here. Depletion capacitance and diffusion also is there. The other one is between base and collector, right? Go back and see, this is the base and collector here. So across this junction here. And there's a diffusion capacitance also. Now I'm showing you that, so N is my collector, P is my base, and E is the emitter here. Besides that, emitter, base, and collector, you also have all of this as a substrate. This is the substrate on which you have made the transistor here. And the substrate I'm showing you is P-type. So if you look at this substrate P-type and you see N here, so you have a junction here also. You have a junction here also, and so there's a capacitance here also. Right? And this, so a bipolar transistor then, if you look at it from this picture, is not just a three-terminal device. Emitter, base, and collector. The emitter, base, and collector are made on top of a substrate. And the substrate is also another terminal, right? And therefore, if I have another terminal, and substrate is usually kept at a large negative voltage. Why do I do that? Large negative voltage and is fixed because you will see in a minute. First of all, you may be wondering, why do I have a substrate at all? Why don't I make this whole region N, right? Why don't I make this whole region N, and then I will have a P and an N and no substrate. The N region serves as a substrate also, right? The reason why I can't do it is, I'm not interested in making just one transistor. When I'm making circuits, I'm making, hundreds of transistors, and they all have to be made side by side. And so look at that. So what you may be wondering is, let the whole region be an N-type. So I have a collector here, and I have a base, an emitter, no substrate, and therefore no substrate capacitance here. But I can't do that. The reason is, as I said, that we have to make several transistors. I have to make several transistors, right? So not just one transistor, but I have to make several. Now, if you make several transistors, what would happen? Suppose I make another transistor here. What will happen? I'll make a P and I'll make a N plus. I have made another transistor, but what has happened is the collector is common. The collector is common for all of them. So I can make, as many transistors as you want side by side, but what happens is N is common for all of them. And therefore all of them share the same collector, and that's not very useful. I want isolated transistors. Isolated means each one has its own emitter, base, and collector terminal. So I can't do that. The only way that is possible is the following. As you can see here, I can make two transistors side by side, but they have the same collector. Collector voltages are the same. And therefore, I can't do this. If I want to make more than one transistor, which is what we have to do, therefore this option is not available. I can't just use my N as a substrate itself. I have to go to this picture here. I have to go to this picture here. So I make one transistor that you see here, E2, B2, C2, and another transistor, transistor 1 here, E1, B1, and C1. Note, the two transistors are made in this substrate here, P. Now, you may see here that this transistor is isolated from this transistor. How? Because between this, what I'm going to do is, P-type that you see here, I'm going to apply a large negative voltage here, so that this NP junction is reverse biased. And this NP junction is also reverse biased. So I have two reverse bias junctions here, right? And reverse bias junctions are what? Like open circuit. Which means what? That this transistor is isolated from this transistor here. Okay, so that's how I make multiple transistors on the same substrate here. I have to use this P region here to isolate this transistor from this transistor here. Okay. Now, some of you may be wondering also that don't I have a N and a P and an N, another transistor here, right? There's an N here and there's a P here and there's an N here, right? Another transistor. But what am I saying? I'm saying I apply a large negative voltage to the substrate, which means what? This NP junction is reverse bias. This NP junction is reverse bias. So yes, you may think that I have a transistor, but in which state is it? Cut off. And so no current is flowing. No current flowing, which means what? This is isolated from this one. Okay. So that's how I make multiple transistors. So you see that I have to have a substrate here. I have to have a substrate here, and there is a voltage applied to the substrate here. So transistor then is not just emitter, base, and collector, but there's a substrate contact as well. Okay. And when I have a substrate contact, then of course I have a capacitance here. I have a capacitance between here and here. So that's the additional capacitance that I have to keep in mind. That between the collector and the substrate, the capacitor. Now note what I'm saying is that the substrate is kept at a large negative voltage and is constant. So if it's a constant, in small signal model, anything constant appears as a ground. Okay, so that's why you will see that when I draw a model, here, I denote a capacitance between collector and substrate, but substrate is at a fixed voltage and fixed voltage appears as a ground. Okay, so you see in a small signal model a capacitance coming here at this particular point here. Okay, so that's the source of this capacitance here. So now you see I have junction capacitance and diffusion capacitance across base emitter. I have between these two junction capacitance between base and collector here, and I have another capacitance between collector and substrate. So these are the capacitors. So now let's make so these two capacitances are in parallel. We can combine them, C pi, and we call it C pi equal to CJE plus C diffusion. So this capacitance, because we have R pi here, so we call it C pi, and this one we call it C mu. There is a different symbol that we use, C mu, for this one here. So my model then becomes what is shown over here. C pi, R pi here, C mu, GMVB, R0 here, and another capacitance CCS here. And the reason why we are calling it pi, you can see that if I start from here, go here, here, and here, it looks like a pi. Okay, so that's why it's the pi model. All right, go from here, here, here is a pi model. Okay, pi representation of a device here. All right, if you want to make things more complicated, you can do that. There is no end to how complicated a model you can make. Now, just to illustrate, I've shown you that there are further resistors here. I've shown you a resistor here called RBB. Where is it coming from? Now note, the model that I just made, all this model here, was referring to this one between these two parallel lines. Right? Between these two parallel lines here. Now, note what happens is, base current starts from here. And starts from here, flows all the way down, flows like this here, and then goes up. Right? So note the path of the holes. Holes will start from here, come down, move here, and then go up. Then go a little bit here, then go up. So what you are seeing is the path when the holes travel here, because it's a semiconductor, it has a resistance. So there's a resistance here. And then it travels laterally also, there's a resistance here. So all this resistance that you see here, one has lumped it up and called it RBB, a base resistance that you see here. So in addition to R pi, there's a resistance RB here. Not only that, well, you can imagine now I should put a resistance in the collector also. Because once the electrons come here, what happens? They go here and then they go up, right? So I should put a resistance in the collector also. Not only that, as the electrons arrive in the N plus, they also go and then reach here. So I should put a resistance in the emitter also. So if you want to be more accurate and do a better design or a better analysis, you have to put a resistor here, emitter. You have to put a resistor here in the collector. And base I've put because amongst all the three that you see here, this is one of the most important. Okay, so I've included this base resistance. Some places what will happen is we'll neglect base resistance, some places will keep it. Okay, you know, the point about approximation that you have to remember is some place an approximation makes sense, another place it doesn't make sense. Okay, so you'll see some places I'm, you know, invoking RBB because if you don't keep RBB, then you get gross error. As an example, suppose you apply a voltage here at the base, a sinusoidal voltage at the base. Okay. Now, if you apply a sinusoidal voltage to the base and you neglect RBB, what does it mean? The sinusoidal voltage goes straight here to B dash and it goes here and therefore it appears across this region here. So whatever voltage you apply here, it will go straight and appear at this terminal here, VB dash E, which means what? This current will instantaneously respond to the voltage here. Whatever voltage you apply, whatever change you cause here, this will, if there's no RBB, it will instantaneously go here and therefore it will travel to the collector. On the other hand, if I keep RBB, you know that there is RBB and then there's a capacitor. It will have a response time. So whatever voltage you apply here, it will take some time to arrive at this one. It will take some time for the capacitor to charge and discharge, right? And therefore, the collector current will respond a little later here. So when you're looking at frequency response, RBB becomes very important. Even though it may be small, it becomes very important for us. Otherwise, you will not get any frequency response. The signal here straight away goes to here and straight away goes here. It just instantaneously travels, which is not true. Okay, so RBB is very important from that perspective. All right, so that completes our model now. We have seen that this is the DC model of a transistor with all the equations that we have seen, exponential equations, early effect here. This is a simplified model where we approximated by 0.7, and this is the small signal model here. Same thing happens for PNP. One thing I want to emphasize is for PNP, the small signal model is exactly the same as an NPN. Exactly the same. The directions of the current sources, everything is the same. Okay, and except in the DC model here, of course, the direction of the diode and the currents and all that change here. But small signal model is exactly the same. Okay. In saturation region, we've already seen transistor can be approximated by a constant voltage between collector and emitter. Okay, so let's take an example. So here is a transistor, which I'm calling it, N type EE210 right? So it's our bipolar transistor for this particular course. Okay, so most of the time when we analyze transistor, it will have characteristics like this here. So I've given a value of IS, saturation current, beta forward is 100, beta reverse is 1, early voltage is 100, RBB, that resistor that you just saw, 200 ohms, will take room temperature. CJE0, CJC0, all of that is given here. M is 0.5, VBI is 0.85, transit time is 1 nanosecond. So that's our transistor. So for homework, for exams and all of that, everywhere, when we refer to NPN transistor, we'll refer to characteristics like this here. Okay, so let's take up this and suppose we use this particular transistor in forward active mode. VB is 0.7 then, and suppose collector base voltage is reverse bias minus 3 volt, collector to substrate voltage 2 volt, we bias it at 1 milliampere, base current then is 1 milliampere divided by 100 is 10 microamperes. Okay, if I build a small signal model now, Let's do that. Once I know the bias point, let's build the small signal model, which means GM is IC by VT, 38 here, milli. R pi is VT by IC into beta, 2.6 kilo ohm. R naught is VA by IC, 100 kilo ohm. So we get our R pi, GM, R naught. Capacitances, C pi, GM tau F plus CJE. GM tau F plus CJE0, 1 minus VB by VBI to the power M. We put all of this together, we get 38.5 picofarad. Okay. C mu, CJC here, we put all of this together, 0.23 picofarad. CJ, this one here, the junction, substrate capacitance, we put its values, we get 1.6 PF here. Okay, so what these are illustrating are typical values of small signal parameters here. You see here GM, R pi, R0. Note the values here. R pi is typically, if you bias it at around a milliampere, 2.6 kilo ohm, R0 is 100K. Look at the values of the capacitance. C pi is much larger, 38.5 picofarad here. Much larger as compared to C mu here. C mu is only 0.2 picofarad here. And this one, of course, is 1.6 picofarad. So these are typical values to keep in mind when we do analysis of amplifiers and other circuits using our bipolar transistor here. Okay. Of course, as you change your bias, if you change your collector current, everything changes here. GM changes, R pi change, R0 changes here. C pi will also change here because this is a dominant component. So as you change your collector current, this also changes here. And of course, C mu and all that here. Okay. All right. Last point before we leave today, very quickly, is how fast is your transistor? And we use a parameter called unity gain frequency here. Let me tell you what this parameter is. If I take my bipolar transistor now here, let's focus on the circuit. Bipolar transistor is here. Collector is connected to some large positive voltage, say 5 volt. And I apply a DC current IB. IB here, DC current. And the DC current will go here. And the base emitter junction is forward bias. Collector base junction is reverse bias here. So the transistor is working in forward active mode. Okay. So that's the biasing. Biasing is done through IB and through VCC. Now on top of that, what I do is I add a small signal, which is a sinusoidal base current. So in addition to this DC base current, I add a sinusoidal base current here. So that's also going to flow. Now, in response to the sinusoidal base current, there'll be a sinusoidal collector current, right? Because collector responds to the base. If there's a DC here, there'll be a DC collector current, and in response to AC base current, there'll be an AC collector current also. So now I'm looking at a specific quantity which I call AC current gain, which means what? AC current here, IC, divided by AC base current here. I'm looking at an AC current gain here, okay? Not looking at DC. DC will be the capital IC divided by capital IB. So this is the AC current gain or the small signal current gain here. And that turns out to be a function of omega, the frequency that I apply here. And what happens is, if I plot, I will see a graph like this. If I go and take a transistor and measure it, I will see that the AC current gain as a function of omega initially is constant. I'm plotting it as in dBs, 20 log 10 beta AC, and this is omega here. This is a log axis here. Initially, beta is constant, but after a while starts falling. Starts falling, and there's a frequency at which it becomes 0 dB, which basically means that IC by IB has become 1. And that frequency people call as a unity gain frequency. This frequency where the AC current gain becomes equal to 1 or 0 dB is called the unity gain frequency. And the claim here is that the transistor is useful only for frequencies less than this particular one. Because many places where, when you look at a transistor and you look at its application, those applications depend on the fact that collector current is much larger than the base current. Collector current is much larger than the base current. And here you're finding that the sinusoidal base current is as large as the sinusoidal collector current. And therefore, you will find that all the circuits that are made using bipolar transistors, they will all fail when you reach at this particular point. because all those circuits are relying on the fact that the base current is much smaller than the collector current here. And now we have collector current, sinusoidal collector current as large as sinusoidal base current. So this is like the upper limit here. In fact, most circuits will have to operate at frequencies maybe 4 or 5 times smaller than the unity gain frequency to work properly here. So this is an upper limit on how fast your transistor is, unity gain frequency. So you will find that when you go and look at data sheets, a manufacturer will say the unity gain frequency of the transistor is 450 megahertz. Or for another transistor, he'll say 100 megahertz or 1 gigahertz. So what it means is that if you want to quickly compare the speed of the transistor, you look at this parameter called unity gain frequency. So now we know that this is a sinusoidal base current, and so we can derive this particular expression using a small signal model that we just derived, and from there find out what does my speed of the transistor really depend on. I can do that, and if I just want to, we'll see it later on. FT then turns out to be using this an expression like this here. Unity gain frequency that you see here, FT, depends on GM, depends on C pi and C mu. So we can calculate what the unity gain frequency of the transistor is. Okay, so let's stop here and